Welcome back. So we're now in the lab cutting, and this week we start an electronics sequence. And this is one of the core classes. So many of the things I casually said you can do come from the power of little embedded computer chips that build intelligence into your projects. And so you're not going to master that in 1 week, but we're going to begin the sequence. And this week is very much an experiment. We're doing it in a new way. So in past years, this week you learned to make a circuit board. Then this week you learned to design a circuit board. And then this week you learned to program a circuit board. This year, we're going to do it in the opposite sequence. You're going to program, then design, then build. And the reason we're doing that is the performance of little processor development boards. The performance has gone up and the cost has gone down so much that we can do it in this order. So it's an experiment, but I suspect it'll be a much easier transition in to get you programming first and then designing and building. Then no recitation this week. The week after that, the recitation will be learning all about programming. So you're going to start programming this week, making little changes to programs, and then making harder and harder programs. And then the recitation will help you delve more deeply into programming. So here we go. The assignment for this week is read a microcontroller datasheet, and then you're going to program a development board to interact and communicate. And then as a group, you're going to compare different architectures. So lots to learn. And again, you won't really master this until the end of the cycle. And really, it'll probably take a few years after that. So this is the beginning of a journey. The journey doesn't end this week. So first, let's see, let me jump to just to have a mental model. This is a $4 module that's a complete development system. It speaks USB-C. It's got these programming buttons. It's got a programmable light. It's got these interfaces. And I'm going to go through in much more detail. Here's a sample program where I'm typing on a computer, and every time I type, I send a message to it, it blinks the light, and it sends a message back to me. So that's in a complete example, I'll explain more, but of a little development board interacting and communicating. So to do that, first off, we need to pick an architecture, the type. And so von Neumann is the architecture on a typical desktop computer. A Harvard architecture is different. This dates back to an early computer at Harvard. In a Harvard architecture, the program and data memory are separate, which is less flexible but can run more efficiently. And a fun detail is there's a famous bug where that computer stopped working, and it was because there was literally a bug in it. There was an insect that got stuck in the computer, and that was an early version of a computer bug. But we're going to be using a Harvard architecture. CISC is, each instruction is complex and can do many things. We're going to be using RISC. RISC is a reduced instruction set by having simpler instructions, the processor can run faster. Then the computer in front of you has a microprocessor. To run, it needs memory and communication and many other things around it. We're going to be using a microcontroller, and a microcontroller is it is both less and more. It's a simpler processor, but it has built in all of the other things it needs to function, like memory and communication. So we'll be using microcontrollers. The cores are the processing units. And historically, there was only one for little embedded systems. Today, we'll see versions that have more than one processing unit. If you want to do a really complex artificial intelligence system, you need still bigger processors. And for those, there are what are called GPUs. And those are larger than we're using this week, but you can embed. FPGAs are field programmable gate arrays. These let you essentially make a custom integrated circuit by having a big circuit that's reconfigurable when you need still more performance. This is a link to what's emerging now are silicon compilers, where you can actually compile a computer chip designed from scratch and send it to a foundry to make. And the cost for that is slowly coming down. And then this is a link to a paper I wrote about future architecture, new ways to think about how you use geometry to program computation. But against that background, for this week, we're going to use Harvard architecture RISC microcontrollers. Next, there's many parts of the system. So the assignment down here, read a data sheet. You won't understand what's going on in the processor until you look at the data sheet. And there's a lot going on. So one of the processors we're going to use is this one, D11C. It's a $1 processor. And this is a link to its data sheet. And the data sheet is 1,000 pages, 981 pages. So I don't expect you to read and memorize all 1,000 pages, but you won't understand what's going on until you take a tour through it. So if we look at this processor, this is the system diagram. In that little $1 chip, all of this is going on. And each of these boxes is a module we're going to study. So one of the boxes, many of the boxes, is memory. There are what are called registers, where you hold instructions that you're operating on. There's SRAM, where you store data, and you can access that quickly. There's DRAM. You access it more slowly, but it's a larger memory. There's EEPROM, where you store data and it remembers it if you turn the power off. There's flash, that is a bigger memory, but harder to program. And that's where you store your program. And there's fuse, which is memory where you store configuration. So there's 7 different types of memory in the processor. Then there are the peripherals. And so that's all of the stuff ringing. So in here is the processor, but all around it are the peripherals. So the ports are what talk to the pins to send signals in and out. A to D is analog to digital. It reads in a voltage and gives you a number. Comparator measures the difference between 2 voltages and just says higher or lower, which sounds less useful, but you can do it much more quickly. D to A is digital to analog. It turns a number into a voltage to send out. There are modules that measure time, that count events, or do a very important thing we're going to be using called pulse width modulation. Pulse width modulation is where you make pulses, and then what you do is you vary the length of the pulse. You make the pulses longer and shorter. And there are many use cases for that. Ricardo's asking, why are there comparators? The comparator, one use for them is if you just want to know a threshold, like is a battery voltage below, too low, or so you can't use it. Rather than reading the A to D and converting it, the comparator, you can just ask it, is the voltage too high or too low? Another use is if you want to convert a voltage very quickly, you can use a few different comparators to compare it. So one is when you want to make simple comparisons for like an alarm, and one is when you want to get a very fast result. USARTs are modules to send messages in and out to peripherals. And so let's see, if we go back to the RP2040, SDA and SCL and MISO-MOSI, S-clock, those are all protocols for chips to talk to other chips that we'll be learning about. Then USB is obviously USB. This is an interface to talk to a USB device. There are peripherals whose job is to do math, to do math calculations quickly. There are peripherals that do cryptography for security. And there are many, many other kinds of peripherals depending on the processor. So if we go back to our data sheet, in the data sheet, this shows you all the different subsystems. And then if you start going through here, like here's the subsystem just on the comparator. And so this describes the comparator. It tells you about the performance of the comparator. And then further down in the data sheet, so here's the block diagram of the comparator. It tells you about how to use it. And then it tells you this part of the data sheet is how to program the comparator. And every one of these subsystems is a section in the data sheet. And so what I want you to do is browse the data sheet just to start getting a mental picture of what all is going on inside. Because you can't understand it just from software. You have to understand the boundary between the software and the hardware. The word size is in the register and the memory, how many bits it operates on. And so the cheapest simple processors are 8-bit. The more powerful ones we're using are 32-bit. Those are the most common. A bigger word lets you do more in one operation, but the little 8-bit processors can still do 32-bit operations. It just takes a few cycles of their clock to do it. So next up, we need to pick the family of the processor. This is a table of a test I like to do. What's going on in this table is I take my processor and I take a pin going out, I connect it to a pin going in, and then in software, I invert it. So I put out a 1. A 1 is here, I read in a 1 here, but when I invert it, it becomes a 0. So I put out a 0 comes in. When I invert it, it becomes a 1. And if I look here, what I get is a waveform, and the waveform tells me how long it takes to go from software to hardware and back again. And if you look at this test, this is in millions of cycles per second, and this goes from 0.02 to 60, a wide range of speeds of these different families. So just for history, this is a fun example. This is a processor made out of cardboard and marbles. This is a crazy room-filling processor made out of single transistors that basically does the same as what you're going to be using that fits on your fingertip. Again, this is history. This is a famous computer chip made by hand in a giant circuit one at a time. These are all just historical examples. This is one of the earliest embedded processors. They're still around, but very old architectures. These were important ones historically. We're not using them. The families we're going to make a lot of use of are AVR, ARM, EXTENSA, and RISC-V. So the AVR family came from Norwegian grad students originally, and they wanted to design an embedded processor that you can use modern compilers on. And so the smallest one in that family is the tiny 412. So it's this little 8-pin processor in the AVR family. And that's enough. In this example, what I'm doing is I'm loading software and and it's blinking the LED. So the AVR family, the tiniest one is this size. This is about the size of a grain of rice. It lets you paste in a teeny little processor. This family is convenient. They're low cost, convenient sizes, and they're very easy to use and understand. The data sheet is fairly simple, and essentially everything it does takes one instruction cycle. And so these are easy to design around. They're very easy to program, and you can use modern software tools I'll talk about. So that's the AVR family. Then the ARM has an interesting history as a company, but it's a British company, and they don't make chips. They make designs for chips that other people use. And almost every mobile phone today uses an ARM chip. And so in the ARM family, we're using the SAMD. The SAMD come from Microchip. And these, this is a 14-pin version. And then these are larger and larger versions. Each of these, let's see, let me show that. These are all in the same family. So that's the D11. This is the D21. And so that's in, let's see, was it 32 pins? Let's see, it's 26 IOs. Yeah, 32 pin package. This is the D51, and that's in a 64 pin package. Each of these adds more peripherals, more memory, and in particular, just more pins. As the projects grow, you can need more and more pins. So the ARM processors, compared to the AVRs, they run at a lower voltage, and we'll see that in the circuits. They can run with faster clocks, and so 48 megahertz is typical. They have more powerful peripherals than the AVRs, roughly, but the issue is this is a much more general architecture. And so if we go back to the D11 data sheet, when you look at the system diagram, these big vertical lines are networks. And so just like the internet is a network, there's a network built into the processor. And so to use it, you need to configure the network for how everything talks. And so it's much harder to program this just from the data sheet typically you use libraries that help you set up the network to be able to configure it. But the ARM processors go from little tiny embedded ones up to the world's biggest supercomputers. So it's a very wide range in the family. And they have good tools for debugging that I'll talk about. So a more powerful family. STM32s are another version of ARMs that are similar to this range. They've got convenient software tools. And then the RP2040 is a really interesting, fairly new processor. So you may already be familiar with Raspberry Pi. Raspberry Pi started by making a single board computer that has a much bigger processor and talks to a video display and networks and runs a desktop operating system. But after many years, they decided to design their own embedded processor. So the RP2040 is a embedded processor. Embedded means a little thing you design into circuits, not building a big system around it. The RP2040, you can already see the data sheet looks different. It's more human readable. It's designed sort of for ordinary people, more ordinary people, not engineers. And the RP2040 is a really interesting implementation. So it's a 32-bit processor. It's much faster than the other ones I said. The standard clock speed is 130 megahertz, but you can easily run the clock faster than that. That's beyond the specification, but there's a range where it'll still work. And so 250 megahertz is a typical number for that. The reason you care is if you want to do things like simple artificial intelligence, where you recognize a sound, for example, or generating waveforms for displays or synthesizers, you're limited by how fast the processor can run. So the faster clock just lets it get more work done. And this is about maybe 10 times faster than the previous ones I mentioned. It has more memory for larger programs and data. And then it has very powerful peripherals. So I described many different kinds of peripherals. This has a very special kind of peripheral that's reconfigurable. So you can write little programs and make custom peripherals for new applications in that family. Now, the RP24 chip itself is too large for you to easily make a circuit with. So if we go to DigiKey, this is what the RP24 chip looks like. So it's got lots of pins. And when we get to electronics, we'll cover these types of circuits. You have to do what's called reflow at a very fine pitch to solder with this. So it's not realistic for a beginner to make a circuit using that. But, and let me leave this one back up. What makes the reason why we like this so much is Seed, our colleagues in Shenzhen, and they've made this really nice module that for size, let me grab one. This is the size of the module. This shows you the size. And so this is the RP24 with, I'll explain what these things are on it, with a USB interface you can use to power and load a program. But this is what's called a castellated board. And so in a little bit, we'll be meeting this. This is an example from Adrian, where what you can do is you can design your circuit board, and then you can just paste this into your circuit board. So you can ignore all the pins on the package, and you can just design a circuit board around the pins. It breaks out like this and paste it in. And so this is simultaneously a complete development system. You can write complete programs and develop them on this. Adrian is showing in the video. Here, Adrian, I'll stop talking. If you talk, you'll get audio, you'll get focus in the video.
Hi. The problem is I have 2 computers. Sorry.
Oh, don't worry then. It's fine. Oh, okay, yeah. Okay, you'll come show it.
Yeah, Adrian is showing the word in the video.
Good. Okay, thanks, Adrian. And so the reason we switched the order is really thanks to these, because this is $4. So you can easily each have one. With this, it's a complete system. This is everything you need to start writing programs. But then you can progress by pasting this into other designs. So this isn't enough to fly a quadcopter, but you can design a board to run your quadcopter or make your kickboxing system, but you can paste this into it, like Adrian is showing here. So that's the RP2040 family. Then EXTENSA is another architecture. Each of these families, they all share the same kind of programs run within the families. This is one that dates back to what's called MIPS. EXTENSA is a really interesting Shenzhen company. And what they did is they took the processor and integrated nice radios and networking protocols. So this is an 8-bit version. Then this is a 32-bit version. And so these are processors that know how to speak to Bluetooth and Wi-Fi and use internet protocols. And we're going to see that in Networking Week. Then RISC-V is probably going to take over the world. ARM, so AVR is just owned by Microchip. ARM sells to many companies, but you have to pay ARM to use the design, and a lot of money. RISC-V is an open design. It's a family of processors, but it's open source. Many people contribute, and you don't need to pay to use it. And so many parts are coming out in the RISC-V family. And the most relevant one for us is the ESP32C3, is a 32-bit processor with Bluetooth and Wi-Fi using RISC-V, and it's also available as a SHAO. And so a lovely thing C did is this has the same package, the same pinout as the RP2040. But this is a version, if you want radios, you can use this version to do the RF communication. And so many new parts are in the pipeline coming with RISC-V. So in your labs is likely a mix of all of these, and all of them are useful. Oh, sorry, Nicholas, there's a SAMD RISC-V. Oh, sorry, no, the SHAOs. No, that's what I was confused. There's a SHAO for the SAMD21. That's right. So all of these are useful. I'm going to mention use cases for each of them, and it's good to be aware of all of them. Then this last group is, these are all versions of multi-core. These are each versions of embedded processors, but these go from tens to hundreds to thousands of processor cores. So you won't use this as a beginner, but again, these are what you use when you need to do really powerful embedded processing. Michael's asking about the Pi Pico. The The difference is just the form factor. So the Pi Pico is a much bigger board with many more pads. And so the Pi Pico is a fine thing to use if you needed all of these things broken out. But for many other purposes, if you're making the drone or the kickboxing, you don't need to embed that board. This has everything you need to talk to it. So it's really just the size of the package. That they're about the same cost and the same performance. Okay, I'm going to mute everyone. Jessel, I'm going to talk about Arduinos and Node shortly. And let me get back to where I'm making notes. Let me add that. So I'm going to talk about that question. That's not a nonsense question. I'm going to talk about all of that. So you have available to you AVRs, SAMD arms, RP20. RP24 is new. Not all labs have them yet, but I recommend them. And then the Espresso family. Next note is the vendors. So there's a consistent cycle that chip companies start making chips and people start buying them. And then at some point, these cross and they have too much inventory or the economy starts going down, so they stop making them, and then you want to buy them, but you can't buy them because they're not available. So then they start making them, but demand starts falling off, and those are forever not aligning. So right now, if you wanted to buy an ATtiny 412, Octopart is a search engine. Oh, actually, look, the 412 is back in stock. It used to be out of stock. Now that's back in stock. And in fact, if we take one of these and you look at the inventory history, this shows you how it comes in and out of stock. And so let's see if we do the SAMD 11C right now, it's just not available. And so the parts you want come in and out of availability, and it's always been true. And so it's a good idea to stock up on these as they become available. Your lab should have supplies, but it's a good idea to stock up on them. Next come the package. So if we go back to Octopart and say take ATtiny 44. So sorry. Sorry, 44A. Okay, this is what I wanted. So this package is through hole, where you push it through holes in the board. We don't use that anymore. You could still use them in breadboards, which I'll talk about in a few weeks. But these are a bigger package that requires drilling holes in the board for every lead. Instead, we use these, which are surface mount, where you only mount them on one side. This one is easy to use. It's easy to make the board. It's easy to solder. This is what's called chip scale packaging, where it's essentially the size of the chip and just a little envelope around that. And so that has pads that are closer together, and you can't solder from the outside. You need to use paste solder. I'll talk about in a few weeks. underneath. And so those let you make smaller boards, but they're harder to assemble. So we're going to be using, these are names for chip scale packages we'll be using. And then these are the tiniest packages. This is somebody using the process you'll be using to make lands for what's called a ball grid array, which is tiny little balls underneath. You can do that, but that's much more demanding. So we'll be using these size packages. So once we pick the processor, now we need to program it. So you're going to use languages to program it. The very lowest language is this. This is what the processor understands. Those are the codes that it executes. Nobody writes those by hand. Just above that is what's called assembly language. So this is an instruction set. So like if we go to the instruction set, one of the instructions is to add 2 numbers. And so this tells you the code to tell it to add 2 numbers. And assembly language is where you essentially just write, you don't need to remember the codes, you can use the names, but you write each instruction out. A long time ago, that was the only way to program these. And so in this class, you would learn assembly language programming. That's obsolete. You don't need to do that now. What are called compilers let you take an easy to understand language and turn it into those instructions. But even so, occasionally when you want something to run really fast, you can still mix in little bits of assembly language, but less and less common. Far and away, the most common language we're going to use is C and the C++. So C is a classic programming language used from the smallest to the biggest systems. C++ extends it with crucial things that were missing in C, including objects, where you can have programs and data together. So we're going to be using C. This is notes on programming that you can browse. This is notes on data types. And let me jump ahead to say, down below, I have examples of programs for all of these processors. You don't write these from scratch. So if we take the RP2040, this is an example to communicate and blink a light using C. This is an example using Python. You shouldn't start from scratch. Start from an existing program and modify it. I don't start from a blank editor. I always take a previous program and I modify it. It's too hard to remember all of this to start from scratch. So this week, you're going to learn how to start from an existing program and modify it, and bit by bit, you'll write more of it. So C is the most common language. GCC is the compiler we use. So GCC takes your program and it turns it into the codes the processor understands. This is a link to, often we're manipulating bits. We're doing very low level stuff, like you're turning pins on and off. And so this talks about programming to manipulate bits. So for the AVR family, there are libraries that let GCC talk to an AVR. And so in Linux-derived systems, this is what you need to install it. In Mac-derived systems, this is what you need to install it. I'll talk about Windows in a moment. And so the main reason the AVR family exists is there's good support for GCC to compile to it, a modern compiler to the processor. For the ARM family, the ARM company itself develops a whole suite of tools for it. So ARM provides tools. So in Linux derived, this is how you install ARM. This is Mac derived. This is a link to a project developing open libraries to support the ARM family. So that's for ARM programming. Then Microchip for the AVR and the SAMD for Windows has a Microsoft Studio. Let's see, that's weird. They edited their site and they made a mistake in the redirect. So I'm gonna have to fix that. So Microchip has a studio. So here's the new link to it. That's a Windows development environment I'll talk about in a minute. And then they also make available tool chains. The tool chain is all the software to go from your program to it for their families, AVR and SAMD. Okay, next up is, these are two newer languages, Rust and Go. You can run them on these processors. Many computer problems of your software crashing, hackers attacking, come from problems in C. In C, you can have what's called a memory leak, where it uses memory but doesn't return it. You can have buffers that overrun that let you steal information. You can have what are called race conditions, where what happens depends on how fast things run relative to each other. These are newer languages that fix those problems. And so these are not as common yet for embedded programming, but they're growing in popularity, and you'll see more of them. Then come the interpreters. So Python is a beautiful language, and instead of compiling, it's interpreted. What that means is you can use it interactively. Instead of just running a program, you can type commands and it'll respond to them. So it's much easier to develop because you can do things with interaction. REPL is the command prompt you use. It's read, evaluate, print, loop. The interpreted languages, though, are much slower. The interpreter is between 10 and 100 times slower than compiled languages. They're also larger. You need more processor memory to use them, but the newer processors we're using can use them. And then this is a link to MicroPython has a number of ways to speed it up. And in particular, what's most important is it can essentially compile so you get the best of both worlds. And so if you go back to the performance table I had up here, so on the RP2040, let's see, yeah, if we take the original Raspberry Pi, this is just doing it in plain Python. On the RP2040, this is 10 times faster using Python, but pre-compiling it. But then way up here, if we continue with the RP2040, is 10 times faster is using C. And then 10 times faster C still is using the peripherals. So that was a factor of 1,000 range on the very same processor based on the language. So Python used to need more memory than the little processors. Now there's plenty of room for it. And the processors have gotten so fast that you can use Python for fairly real-time things. So this will be growing in importance. And so for this week's assignment, you can choose to do it in C or Python. And then these are links to embedded JavaScript. So given all the web development, this lets you do JavaScript development in embedded boards. It's fine. I much prefer Python as a language. It's a really beautiful language with a much bigger ecosystem around it. And so Python was less common in projects like we'll do in this class, but it's growing in importance. Okay, so you'll pick a language. Most likely it'll be C or Python. Then now we've got our processor. You need to get your program into it. So in system development is how you load code into it. The original AVR family used what was called ISP. These parts aren't quite obsolete, but they're 2 generations back. So unless your lab already has these, I wouldn't use it. The newer AVRs, which are cheap and cheerful and convenient, they use what's called UPDI, which is 1-pin programming. These are different versions. Let's see. This converts USB to serial, and then this converts it to UPDI. This one does it directly. So this takes a USB signal on this side. On this side, it makes UPDI. And then if we go down to the tiny 412, on this board, this pin brings in power, and then this brings in UPDI, and that's what we use to load a program in it. So if you're using an AVR, a current AVR, you use UPDI. If you're using an ARM part, it uses what's called JTAG, and that's a standard for communicating to load programs and debug. And SWD is a subset of it that we're using. And so for the D11, here's a board that has a D11, and then it has a header we use to load a program. And with that program, we then load the program, and then we blink the LED. So if you're using, oops, I closed the wrong tab. If you're using the ARM processors, you need a SWD programmer. And now the really fun thing here is this is a programmer. You can program to be a programmer. So this is a D11, one of the ARM parts you can use. On this side, you load a program into it, and you only have to do that one time. You teach it to be a programmer, and on this side, you can program. So you can use this to make a JTAG programmer for an ARM part. And previously in this class, Adrian is showing one. Previously in this class, we had everybody do that. This week, you made a programmer. The reason we're not doing it is what comes next are bootloaders. So this is a link to Atmel's bootloader. This is a link to Arduino bootloaders that I'll talk a lot about in a minute. A bootloader is a program to load programs. And so inside the shell, and we'll see this in a minute, it has a built-in bootloader. And so you don't need a programmer. It can communicate over USB. And usually over USB, you're just sending and receiving messages. But you can send a special command that tells it to take a program over the communication port. So a bootloader is a program to load programs. Once you have a bootloader, as long as your processor can communicate, you don't need another program. And so for this week, likely rather than a programmer, you're going to be using a development board that has a bootloader built into it, and you're going to learn how to put bootloaders into your processors. So for in-circuit development, we'll be using bootloaders. So then next is, now we have a programming language, we have a way to load it. you now need a way to write the program and tell the processor to use it. So integrated development environments, IDEs, let you do that. So Atmel has the studio. Eclipse and VS Code are general purpose programming environments, and you can configure them to talk to embedded processors. Thani is a really nice one specific for Python that we'll be using. Platform IO is a very general sort of platform of platforms that can talk to many different families. And then we get to Arduino. Arduino is a subject of great confusion. Arduino is 6 unrelated things that all get called Arduino. So if you say Arduino, the thing that comes to mind looks like this. So what's going on there is there are boards that are called Arduino boards, but these are like, this is $27. The processors we're using cost $1. So rather than buying an Arduino, you're going to learn to make Arduinos. Second, Arduino is a way to install a tool chain. Each of these tool chains you need to set up. When you install Arduino, it brings with it the tool chain. So Arduino is an easy way to set up a tool chain. So typically, when you're using an Arduino programming environment, you're actually calling GCC. You don't see it directly, but you're calling GCC. Third, you can talk directly to the peripherals in the processor, but typically you use libraries to help you with that. So Arduino is a set of many libraries, some of which are really nice, and some of which are also fairly inefficient, and I'll show examples. Arduino is a development environment that lets you type the code and load it. It's a particular bootloader you can use to get it into the processor, and it's a form factor for plugging in headers on the board. So those 6 things are unrelated and all get called Arduino. You might use a commercial Arduino board this week, but you're going to learn to make your own Arduinos with a $1 processor, and you can use the Arduino tool chain, but for a range of target processors, you're going to mix their libraries with other libraries. We'll see many different IDEs, many different bootloaders. Now, the next big confusion is Arduino is C. When you're writing an Arduino program, you're writing a C program. It's frustrating. You'll hear people say, I don't want to use C, I want to use Arduino because that's easier, more friendly. Arduino is just C. It's C with libraries. This explains how that works. So you're just writing C. Now, the original Arduino used the 328P processor. That processor is long since obsolete. So these are versions of original Arduinos using it. But the really nice thing that happened is an Arduino Core teaches Arduino to talk to a new processor family. And there's many more recent ones. So this is an Arduino Core with a collaborator that talks to the newer AVRs. Quentin, Fab Academy, let's see, Quentin, are you on now? He's at a conference right now. Quentin is a Fab Academy instructor. He maintains the core for the SAMD that lets you from the Arduino talk to that. Espressif has cores for the chips with radios. And then the RP2040, this is the core for that. And there's a nice person who supports it. And I've helped him. I've added some things to this core, helping him speed it up. And so that's what we use to talk to the RP2040s. So even if you never use Arduino for its libraries, I still find it's the most convenient way to install the tool chain. So when you install each of these cores, it brings the whole tool chain for you. Okay, next up is development boards. So we've talked about the shells. And so the shell, there are shells for many different processor families. Each of these has the processor, some local interfaces, and a communication interface. These are all versions of commercial dev boards you can buy. But then if we just take Adrian's example, here's his version of a dev board with the shell. Here's a version with the SAMD. Here's a version with the AVR. In each case, breaking it out, making a number of interfaces. So in next 2 weeks, you're going to design one of these. In 2 more weeks, make it. You can make these in your lab. These are all versions of development boards. I realized I didn't mention one important link, which is Quentin did this. If you're using a bootloader, you only need to load it once. So Quentin made these nice tools that let you physically mount the processor just to load a bootloader in it and then put it in your circuit. And we'll talk more about that in the coming weeks. So this week, the spirit of this week is really doing this week first is driven by the shells. So these are complete little low-cost dev boards, not $30, but $4 that have everything you need to do. But you could use any of these dev boards, or you can use these dev boards you can make in the lab. And then in the coming weeks, you'll be designing them. Okay, still more to cover. Operating systems. Bare metal is where nothing else is going on. You write the program. Operating systems, the main thing they let you do is manage multiple tasks. So these are embedded operating systems, but you won't need these typically until you move to a bigger processor doing much more complex tasks. You won't need these. The processor has a clock to tell time, and typically these use what are called phase lock loops. And so overclocking is where you run the clock faster than it's specified for. And it's not guaranteed to work, but typically it does. And so the RP24s are easily overclocked. Underclocking is where you slow the processor down, and that makes it run more slowly, but what it does is it saves power. And so it's something you do when you want to save power. Now, if we look at the example for this week with the RP2040, I'm going to come back and do this in more detail. This is 2 different programming environments. Here's the chip, and over here is a terminal. And so over here, what I'm doing is I'm typing commands on a terminal, and what I type goes in through USB, and it talks back to me. So if we take that example, I'm using a terminal to communicate. So Arduino has a serial monitor. These are 3 different programs. Screen is a convenient program. This is a Python. This is a JavaScript. This is for browsers. All of those let you send commands to and from the processor. And so with all of that, now we can start drilling in on examples. So this example, let's see, if we come back to the Arduino core, are you asking about, well, the CPU core, I'll talk about, Ricardo. So hold on that. If you want to use the 412, here's an example of a tiny little dev board. This is a version of an Arduino program, which is a C program. So pins can be inputs or outputs. I have to tell the pin to be an output. I write a signal out, I wait, I write a signal out and wait. That's with Arduino. This is a version without Arduino, just simply writing a C program without the Arduino libraries. So those are examples for the Tiny 44s. These are examples for the D11. So this is a board. I bring the D11. the smallest one, the most convenient thing is it speaks to USB. So I bring in USB. USB is 5 volts. I have to convert it to 3 volts. That's what this part does. Here's an LED, and this resistor limits the current going through the LED. And this is to load the program. And then with that board, here's a similar looking Arduino program to blink the LED. That's with the D11. But I'm going to spend more time now on the RP2040. So in the shell, there's a user LED you can blink. There's another, what's called a NeoPixel. We'll talk more about this in a few weeks, that can be any color. There are these pins, and the pins do multiple functions. They can have digital signals, analog signals, communication signals. And then there's 2 buttons. One button resets the processor, and one tells the processor, reset just restarts it, but it does whatever it was doing. Boot triggers the boot loader. And so when you want to load a program, when you want to load the bootloader, you use that button. And I'll show you that in a few minutes. So here are 2 programs. This one is an Arduino program. And so it means you go to Arduino. If you go to Arduino, then from here you can download the software from Arduino. And then in it, you need to install the Arduino Core. And so that's this one. And so in this Arduino program, I'm using a library to talk to the NeoPixel, you'll see in a minute. These define some values. I've got one of these pixels. These are the pins I'm using. This is where I'm going to store a message. This is a counter. Then in here, I'm setting up. So I'm telling it to communicate over serial, tell it to talk to the pixel. This sets up the pixel with power. Then I'm going to run a loop. And, oh, let's see, I realized, let me make a note. I'll explain in a second. This is a loop, and it just keeps spinning. The setup is done once, the loop runs continuously. And so here, what I'm going to do is ask, is there a character available? A message that came in. If it did, I read the character. I save it in a buffer. Then if I overflowed the buffer, I move back to the beginning. Then I say, here's what you typed, and I type back the buffer. Then here I make the pixel red, green, blue, white, black. I turn on the pixel and I delay. And I realize that there's a typo here. The second line should be delay. I'll fix that. Doesn't really make a difference. And so all of that, let's go to the video now, is if we go to the RP2040. So now I'm going to go to the video. So let me do it more slowly. So here I'm in the Arduino IDE. I have to tell it what board I'm using. So I'm using the shell. I have to tell it what library I'm using for the pixel. Okay. Now, what I'm going to do here is I'm going to hold down boot. I'm going to reset it while holding down boot. And then that triggers the processor to restart everything, to go back to scratch. And then the way this is done is it actually appears as a file device. So I have to pick how it's connected, the port. and it knows it's a file device, and I load the program. And the first time I do that, the Arduino library knows it needs to set up the bootloader. Now, if I go back to port, it's actually changed. Now that I've got it set up for Arduino, it appears as a serial device. So now I'm talking to it and I'm typing, and every time I type, it's sending characters back to me, and it's blinking the RGB LED. So all of that is using the Arduino IDE to load a program into the RP2040. Now I'm going to do the same thing with Python. So MicroPython and CircuitPython are closely related. Both are nice. Either is fine. I'm going to use Thani, which is a nice Python environment. So I'm going to reboot the processor from scratch. Hold down boot, load, reset. Then I'm going to go to Thani. I'm going to go to the options, and I'm going to tell it to install MicroPython. And the Pico is very similar to the Shao, so I can use that as the description. So it just installed a huge program, which is Python, that's now going to be running, interpreting my program. So what I'm doing here is I'm typing commands. So just now what happened is I asked for 1 + 1, and then I asked it to import a math library, and I calculated a trig function. This is using what I call the REPL, the command prompt. I'm typing commands in, and in real time, it's interpreting them and acting on them. So that's using it interactively. Now I'm going to run a Python program. And so I'm going to tell it, well, first what I'm doing is, this is a library I need for the NeoPixel that I've got stored on the processor. Now I'm going to run my program. And so now this is doing the same thing. I'm typing characters and the light is blinking. So if we look at that program, here's the Python program. So these are some Python modules I need. This is for the NeoPixel. Here are the definitions again. Here I'm setting up the pins. It looks very similar. Then here I'm reading from the USB in, I'm saving it, and I'm writing it out, and then I'm blinking. Now already one difference you can see in the C case, I had to allocate a buffer and keep track of where I was in the buffer. In the Python case, it's more convenient. I just add a character to a string and it puts it on the end. Things like that are easier in Python, but they use more memory and they're slower. Mikhail, Python is about 100 times slower than C. You can speed it up with the native command I showed, but even then it's maybe 10 times slower. So plain Python is 100 times slower. With various tricks to speed up Python, it's 10 times slower. And then there's very specialized things you can do to make Python get near C speed, but it's always slower. Now for CPU cores, I realize I didn't show you. The RP2040 has 2 cores, and the really neat thing you can do is this. This is setup and loop. And it also has setup 1 and loop 1. And all you need to do to program the 2 cores is, instead of using loop, use loop 1 in Arduino. And in that case, you're talking to the second core. So it's that's all you need to do to write programs for either cores. So all of that is programming in Arduino and in Python for the RP2040. Then I have examples of doing that for the ESP8266, ESP32. I didn't get a chance to do it for the Shao, but I'll add an example for that. Okay, 2 final important topics. When you start making your own programs, you're going to make a circuit, you're going to load a program, and it won't work. So a big question is how you debug. And we're going to have a recitation on debugging in March 13. So one part is debugging hardware. But in software, you need, so Ricardo, setup and loop both are for loop. There's setup and loop and setup one and loop one. And you can separately set up and program the two processors that way. So once you have an LED you can blink, you can use the LED to help debugging just by putting blinks into the program. Once you have a processor that can send messages, you can put in print statements to tell you what it's doing. But more powerful is embedded debuggers. So GCC is the main compiler we're using. This is a debugger. And what the debugger lets you do is, rather than running the program continuously, you can run the program and you can stop it and you can check memory and read what the memory is doing, change some values and restart it again. And so in-circuit debugging is a more powerful way to figure out what your program is doing. Okay, last topic in the last few minutes is a huge topic. So ChatGPT is all over the press as a large language model. It used to be free, so many people are using it. Now it's not available, increasingly not available free, and you have to pay to log into it. But it's trained on all of language, including, let's see, Charlotte is noting debugging, some debugging also in Arduino too. ChatGPT is a large language model that you can do almost anything with. But in particular, you can ask it to write programs for you. So you can ask it to write a program for an RP2040 that blinks an LED, and it'll write it. Then GitHub is the main open source program sharing platform. Copilot, it was bought by Microsoft. Microsoft is a big investor in OpenAI. Based on that history, Copilot is an AI engine in GitHub. So you can use these to write code for you. If we go back to the agreement you signed, there's a clause in the agreement. Let's see. Let's take a minute on that. The markdown doesn't open in the browser, but if we go to site, students, you need to report attribution of work, both human and machine. And what we had in mind is you can use ChatGPT and Copilot to work on code for this week. And that's increasingly part of programming. But there are multiple notes. The first is these AI engines can write code, but often the code is almost but not quite right. Often the code has bugs in it. So you can't just use the code from them blindly. You need to review the code to understand what it does. Second, the AI engines hallucinate, meaning it's possible to ask them for things, and rather than saying, I don't know how to do it, they'll make stuff up. So it's possible to ask for like a particular processor and peripheral, and it'll make up an answer that's just wrong. And the third thing that's really nasty and the subject of serious lawsuits is they can also steal material. So what's been emerging is the code they give you can be copied from code with copyrights. And even if it's open source code, open source, we'll talk about this later, needs to have the license that travels with it. And so they can give you code that's not free to share without a license and not tell you that. And so all of that's to say, it's a good idea to experiment. Yeah, Jason is also noting there's really nasty stuff about implicit bias and how the AIs were trained is a very serious issue. So I encourage you to experiment with these. These are growing in importance in programming tools. Likely more and more of programming won't be starting from scratch, but using these AI engines and shaping what they do. But you need to be aware of bugs, hallucination, copyright infringement as you use them. Okay, so with all of that, browse through a microcontroller. Don't read every word on every page, but flip through all 1,000 pages just to get a sense of what's in the processor. Then program a dev board. And it can be any board in your lab, but the goal this week is to get you going with the tool chains. And so you need to anticipate in 2 weeks, you're going to design your own dev board. In 2 weeks, you're going to make your own dev board, and then you'll be using those in your projects. So for this week, you should pick a processor that you're going to be using the toolchain for. Then I wanted to do something local. It can blink a light, it can read a button, something that involves something happening locally to the processor. And then I wanted to communicate. And the most straightforward thing would just be USB messages. If you want to look ahead and you use the processors with radios, it could also be Wi-Fi or Bluetooth. But exactly like the example, I want you to see software that communicates and software that interacts. And then do that with one combination. For extra credit, you can try a different language or development environment. So like if you're using C, do it in Arduino, but then do it outside of Arduino, for example. Or if you use C, go to Python. And then as a group, you don't all need to do it, but as a group, it'll be interesting to compare C versus Python speed, AVR versus ARM versus RISC-V. See how many different, if you want to get ambitious, go ahead to FPGAs. See how many different combinations of processors and development environments you can use and compare the performance. Okay. Any final questions? So any of the processors I mentioned are fine. So yeah, the trade-offs. In the Xiao, let's see, I would pick AVRs if you want something that's easy to program from scratch and something that's available in the smallest packages. I would pick SAMDs if you want chips that are easy to solder in your own boards with things like USB interfaces, and they have very good library support. I would pick the ESP32 if you want Wi-Fi or Bluetooth. I would pick the RP24 if you don't want Wi-Fi or Bluetooth, because the RP24 is a faster processor and it's got these really interesting programmable peripherals. So all things being equal, if you had to pick one thing and you have access to the RP24, I would pick that. It's really fast. It supports many languages, really powerful, really configurable. If you know you want radios, I would pick the ESP32. If you're looking ahead to final projects, now RP24 plus Wi-Fi is the Pico, but the ESP32C3 is the processor with the radio built right into it. So RP24, fastest, most powerful overall, ESP with the radios. For the RP2040, you need the Xiao form factor to paste it into your project. the SAMDs are convenient. There isn't much use case for a SAMD in the SHAO, because for the SAMD, you can just buy the processor itself and paste it in. You don't really need it in this package. I would use the SHAOs for these processors that come in much larger footprints. Okay. And so finally, this is an experiment. We've never done it in this order. We'll see how it goes. And let me remind you, I don't expect you to start from scratch. So like for the RP24, I've got these two examples. Start from existing code. It's a little bit like the AI, but now better. Start from known working code and modify it. So you could make the processor play a game this week, or pick interesting ways to interact, or start writing code that just emulates what your final project will do. And then that'll get you started. Then once again, the recitation, not this Monday, but following Monday, will be a deeper dive into programming, filling in more deeply about programming. Okay, happy programming. This class will start. Oh yeah, Henk is noting you can play Doom on the RP2040. We're starting today. It'll take years to fill in everything to know about this, but the journey of embedded programming starts today. Okay, I look forward to see what you're going to do. Remember, open time on Saturday for any kind of help. Okay, see you next week. Bye-bye.
Thank you. Thank you.
Gracias, Ney. Gracias a todos.
Adiós.
Nos vemos.
Gracias, hasta luego.
Chao.
Thank you.
Hasta luego.